Let's go to Code Milkers. Let's check out day 13, 12. Check it out. Contiguous array. Given a binary array, find the maximum length of a contiguous subarray with equal number of 0 and 1. Okay. Find max length of contiguous subarray with equal number of 0 and 1. I'll put a little thing here. Array is binary, meaning only zeros and ones. And contiguous means that the elements must be like in order. Like they you can have disconnected parts. Like if it turned out that elements of 0 and 1 and then the elements at 4 and 5 together, all 4 of them made a subarray with an equal number of zeros and ones, that wouldn't count because it's not contiguous. It doesn't continue. It's not a sequence within the array which is continuous without any breaks in elements. I'll just say the elements must be next to each other. It kind of explains it. It's not too specific, but it kind of gets to the heart of it. Examples. These are pretty short examples, so we might not be able to glean much from it. 0 and 1 returns 2 because the longest continuous subarray with equal number of zeros and ones is 2, which is the entire subarray itself. Doesn't really help much. 0, 1, and 0 is also going to be 2 because we've either got 0 and 1 or 1 and 0. It's not 0, 1, 0 because that would mean there's 2 zeros and 1, 1, so it's unequal. So I gotta think of another test case for this just so I can play around with it. Let's do 0, 0, 1, 0. Wait, no. Let's do 1. Okay. And that is going to return. Let me just do this visually, looking at it. The problem is that this array is going to be huge. It's going to be up to 50,000 elements. So the brute force solution I have in my head, I don't think it's going to work because it is a huge array input. So this 0, 0, and 1, that's not it. 1 and 0, that's not it. We go to the end. 1, 0, 1, 0. So long as it's 4, because of 1, 0, 1, 0. So one pattern I'm seeing in this is that since the number of zeros and ones must be equal, the return value will never be odd because it has to be even with an even number of zeros and ones. So if no matter what, the return value will be even. Something to think about. Data structures. I think no matter what, I've got to be able to do this in linear time. So going over the array once in its entirety. So got to be O of n. And I think I could do O of n space. I think it's possible. So data structures, let's see. It's nice that there's only 2, it's binary, so there's only zeros and ones. It simplifies it. I have to have a way to keep count of the current, I guess the current count of the current subarray. So like, are there equal number of ones and zeros currently? So 0 and 1 have to represent different values when seen. So like 0 could be +1 and 1 could be -1 or vice versa. So then like if you get, let's say 0 is -1 and 1 is +1. So if we got 0 equals -1, 1 equals +1. In our example was 0, 0, 1, 0, 1. The first element makes our count -1. Second makes it -2. Third makes it -1. 0 makes it -2. And 1 makes it -1. Okay, so we have a count. This is definitely the hardest problem, I would say, so far. Just most of them I could think of a solution within this amount of time, but this one it's not too clear. I think I'm on the right track with this counter though. So is there any pattern I can see between these iterations? So on the first loop we have -1, then we go again -2. When we, okay, so this is an interesting one. So the first possible subarray in this example is 0 and 1, because there's 1, 0 and there's 1, 1. This happens when we repeat a count. So -1 was repeated, and so length equals 2. I'll figure out some way to compute the length, but I know length of there is 2. Then at -2 we repeat again. Is there another length we can get from that? Yeah, -2 is repeated. Length is again 2, because as we can see here, 1 and 0 is the -2 count, and this one is the -1 count. And then here, -1 was repeated again. And what is our length that time? 0, 1, 0, 1. So we have length 4. So it looks like from the first index that we mark as a certain count, so the first 0 is at index 0 and the counter is -1. So the first time we see -1 is at index 0, and the first time we see -2 is at index 1. So when we repeat -1 again, can we get the length with those indices? Well, what's the current index of this value? It's 2, so it would be 2 minus, what's the first index? 0 equals 2. Okay, that works for that one. Let's try for -2. For the count -2, we come back to the -2 count when we get to the fourth element, 0, which is our third indexed element. So we would do there 3 minus, what index is our first -2 at? It's at 1. 3 minus 1 is 2. So no change in the length because they're the same. Let's go 1. So the last element, the fourth indexed, is 1, which means we add 1 to the count, which puts us at -1. Then we check the index of the first -1, which is 0, and we subtract that from the current index, which is 4. 4 minus 0 equals 4, and we have our answer. So how would I store these indices? So it looks like so long as the current count has not been used, we should put it in the object. I'll say hash map from here because that's really the data structure I'm thinking of. So in the hash, we would store unseen counts with the current index, because we know that if we reach a certain count again, that means that it balanced out. So that means that either a 1 came into the stack or the 0 came into the stack, meaning that we balanced out the numbers of 0s and 1s if we reach that count again. For any count, 0, -1, 1, etc. So going with an object, it's really a hash, to store, I'll write like this, count and index. Let me see if this works for that first one, for like for a 2-element array. So we have 0 is -1. Then we have 1 is 0. And 0 hasn't happened yet in the array, so we have no index to compare it to. But we can't say that 0 is at index 0 because the element at index 0 might be -1 or +1. So well, for subtracting here, let me just play this out in this iteration. So we'll assume 0 is repeated, because if it's 0, we know there's an equal number of 1s and 0s. We can't start off with, well, no, I guess we do start off with 0 if there's no elements. As soon as we add an element as soon as we go to the first element, we're already off balance because there's only one element. So we have to be at least 2 elements before we can be balanced at all. So the 0 does exist before. 0 does exist in the hash before we actually start iterating. It has to. It has to exist. Because we can't assign the element or the index 0. We can't give that 0 because it's impossible. Because the element at index 0 can't make the subarray balanced. It literally cannot do that. So 0 has to be in our hash before. Let's see. The length of this one will be 2 for 1 and 0. For the subarray with the length of 2, it has to be 2 there. So how could we get 2 from that? Let's see. So we are at index 1. We need to subtract something to get 2. So it's like -1. So I'm going to go with this assumption that if I start the hash with count 0 pointing at -1, I'm going to assume that's going to work. It might not. So it might not. So I'm going to write how it's actually going to look. It's going to look like 0, -1 to start with. And then for each new count, if it exists in the hash already, we check if the subarray between the two indexes, index pointed at by the current count and then the index of the current element, if that subarray's length is greater than the current length we already have, which is going to start out at 0, if it's greater than that, we reassign it and then we go to the next element. If the count does not exist in the hash, we need to add the count as a property and the index as its value. Okay. And since we're only using a hash and the hash is only going over it's only storing something for each element of the array, it should be linear space. So it should hold up my assumption we can do this in linear space. So algorithm, we need to init var for length 0. We need to init var for hash. We're going to assign that 0, -1. Next, for loop. We're going to start at I = 0. So if count, I'm going to go with 0 being -1 and 1 being +1 because it worked well in my examples here when I was working out, forming a mental model of it. So we're going to leave it like that. We also need a init count var. Count is equal to count plus -1 or 1. So if hash count exists, this count is equal to index. Here we're going to say length is equal to the maximum, max of length, or the hash count. Well, it's actually first the current index, so index minus. It's not the current index. It's the. Oh, it is. It is the current index. Yeah, the current index minus the index held by the count property is the length of the subarray. Okay. And then finally we return the length. Okay. This process should work. It makes sense in my head, and it is corroborated by this test case and this test case. So we'll see if it works. Let length equals 0. Let hash equals and let count equals 0. We're going to start count at 0 because that's where it starts. It's balanced to begin with. Once there is an element included, once we iterate over the elements, it gets unbalanced and then rebalances as we go through. So for let I equals 0, I is less than nums.length. I plus 1. And we're going to return the length here. Okay, so count is equal to, we're going to use the ternary operator here. Nums I is equal to 0. And count we'll do count plus equal to either -1 or 1. Now, I want to see if that is actually outputting the correct count. Nice. Let's try it with 0, 0, 1, 0, 1. The test case we made up. Yeah, that's good. Okay. So if you haven't used the ternary operator, basically you're saying the left-hand side of this, so count plus, count is going to be reassigned to count plus the return value of this expression. So if nums I is equal to 0, it's going to be count plus -1. If not, it's going to be count plus 1. So if hash count is equal to undefined, we want to do hash count is equal to I, and then if not, we want to do length is equal to math max, and it's either the length or I minus hash count. All right, that worked. Okay, that worked very nicely. Let's try one with just a single element, one with no element, and then a longer one. So let's do 1, 0, 0, 1, 0, 1. So this one should be 6, this should be 0, this should be 0. Great, okay. It looks good. Let's just throw one more in. 0, 0, 0, 1, 0, 0, 1, 1. So this one, the length should be 6. Yeah. Okay, let's try submitting it. Woo! That was a doozy. Okay. Not too fast. I thought it would be faster because it's linear, but some people must be like using some dynamic programming, memoization stuff with this. I don't even know. Well, I'm satisfied with it. Thanks for watching. Have a great day.